This week, we'll be learning about correlations and bivariate regressions. We'll start with a review from the last 2 to 3 weeks. When we have a p-value, the p-value stands for probability. Thus, the p-value tells us that the probability of something occurring. So specifically, what does this mean? What is the probability of what's occurring? The probability of you getting the exact number, that t-value, by chance or due to random sampling error, when in reality there is no difference, or if the null hypothesis were true. So there is a 2.7% chance 20 randomly selected CBU students will have a GPA of 3.5654, when in reality, the mean GPA of CBU students is a 3.43, or that of the University of Memphis students. So the null was that CBU students would have the same population mean as U of M students of a 3.3. So there's only a 2.7% chance of randomly selecting 20 students and those students having a 3.5654, when in reality there's no difference. We've covered 3 different types of t-tests: one sample, which compares a population to a sample; two sample, which compares 2 independent groups, such as males or females, tall people or short people; and then dependent samples, and it compares 2 sets of information that are related, i.e. like a pre-test, post-test, someone's 4th grade math score compared to their own 8th grade math score, twin A versus twin B, and in all of these we're comparing our P to our alpha. So this week we're going to talk about correlations and bivariate regression. So we'll start with correlations, and researchers compute correlation coefficients when they want to determine how 2 variables are related to each other. The Pearson correlation, which is represented by rho, is the statistic that indicates the association between 2 variables measured on an interval or ratio scales. So these are 2 continuous variables, and we want to know how related they are. There are 2 things that a correlation can tell us. It tells us the direction of the relationship. Does one variable increase as the other increases, or does one variable increase and the other decreases? And the strength of the relationship, how much the variables are associated with each other. So we use a correlation to determine how 2 variables are related. The Pearson's correlation, which we'll be learning about today, is the association between 2 continuous variables, and it tells us the direction of the relationship and the strength of the relationship. So a positive correlation indicates that as the values increase on one, they will increase on the other, or as values decrease on one, they also decrease on the other. So the variables are going the same direction. If one's increasing, the other's increasing. If one's decreasing, the other's decreasing. So if they're going the same direction, that's a positive correlation. On the other hand, a negative correlation is when one variable increases and one variable decreases. So as income goes up, stress levels go down. So that would be a negative correlation, where a positive correlation might be as income goes up, spending habits go up. Okay? The direction of the correlation also could be no correlation if there's no discernible pattern between 2 variables. It's virtually impossible to predict an individual's test score simply by knowing how many hours the person studied for an exam, right? Okay, so on here we can look at our scatter plot and we can see that, we have one student who studied for 2 hours, yet they made a 50. We have another student who studied for 1 hour and made a 95. We have a student who studied for 9 hours and made a 55. So there's no correlation between hours spent studying and scores on the exam. We do have some specific terminology for scatter plots. The x-axis, that is your horizontal axis, is called your predictor variable. So this is, a lot of people might call this the independent variable, but that's incorrect. It's the predictor variable. The y-axis is called the criterion variable. Some people call it the DV or the outcome. So in the example of hours spent studying and exam scores, which is the predictor and which is the criterion? Well, the predictor was the hours spent studying because that's what we're using to predict the criterion variable, exam scores. A correlation tells us the direction, positive or negative, and the strength or magnitude of the relationship. Is it a really strong relationship? Is it a really weak relationship? Or is there no relationship at all? So a correlation can range from -1 to +1. The closer that number is that you'll get in R to 1, either positive or negative, the stronger the relationship. If it's 0, that means there's no relationship. Okay? So the more dispersed the data points are around the line of best fit, positive and negative correlations are equally as strong. So an R of -0.5 is just as strong as an R of +0.5. Okay? So if R equals 1, it's a perfectly positive relationship. As 1 increases, so does the other in a perfectly predictable amount. If your R is -1, it's a perfect negative relationship. As 1 increases, the other decreases by a perfectly predictable amount. And if R is 0, there's no relationship at all. Okay? In social science, we almost never have perfect correlations. Okay? Do not confuse strength and direction. Okay? The signs plus or minus only communicate the direction, not the strength. So of these two, a -0.75 or a 0.5, which is stronger? The -0.75 is stronger because it's closer to 1, negative or positive, the absolute value of 1. Which is stronger, -0.5 or 0.5? Neither. They're the exact same strength in that relationship. Cohen in 1988 created some standards that we use to determine if something has a weak, moderate, or strong correlation. So weak is going to be anything between 0.00 and 0.2, positive or negative. Moderate is between 0.2 and 0.5, and strong correlations are above 0.5. However, this is just a rule of thumb. Sometimes stronger correlations are going to be much higher at 0.9, 0.8. Sometimes you might even consider something to be a weak correlation at a 0.3. But as a rule of thumb, that's a good standard to go by. So just looking at this, these are going to show us some different variations of what you might look like in a scatter plot with each of your correlations. So a correlation of 0.9, pretty strong relationship. As one is increasing, the other is pretty much following that cluster straight up on the other variable. As we jump to a 0.5, we can see it's still a pretty discernible pattern. As one is going up, the other is also going up, but we do have some outliers here. A correlation of 0.1, on the other hand, yeah, you can barely see that as one is increasing, the other is increasing. Okay, so you can see that the closer they are to 1, positive or negative, the stronger that relationship is and the closer all of the data points will be to a straight line. So the Pearson's correlation, again, it examines the relationship between two continuous variables, and we use rho to represent the correlation coefficient, and that expresses the direction and the relationship. It expresses the direction by being a positive or a negative number, and then it indicates the strength of the relationship by how close that number is to 0 or 1. Our variables are either the predictor, which we would think of as the independent variable, and it's continuous, and the criterion, which is our dependent or outcome variable. So some examples of a correlation might be, we want to know if the number of hours of training is associated with a runner's time on a half marathon, or we want to know if the amount of calorie consumption in a day is related to weight gain. So it's very important that this is talking about the relationship or the association between two variables. An example might be hours spent studying and exam scores, and we can use the correlation to examine if these are related. So we have each student has a variable on X, hours studying, and each student has a variable on Y, exam score, and they are matched. And once this is done, a person can then determine on average how many hours is spent studying relative to exam scores. So when we are interpreting correlations, what we're asking is how much variance is shared by two variables. Now remember, variance is a measure of how dispersed scores are. So imagine you have two sets of quiz scores. We have a 1, 2, 2, 3, 5, 8, 9, 9, 10. And it has an average of 5. And a 4, 4, 4, 5, 5, 5, 6, 6, 6, also with an average of 5. The first set has more variance, right? Because those scores are more dispersed than the second set. And we can represent variance in a correlation using a Venn diagram. So the variance of X you see on the left side and the variance of Y on the right side, and however much they overlap is their shared variance. We can also use the squared correlation, or R squared, and this gives us the percent of variance shared between the two variables, and this is a measure of effect size. So if you find that the correlation of savings and income is 0.5, your R squared will be 0.25, and we can interpret this in a number of ways. Income explains 25% of the variance in savings. Savings and income share 25% of variance. Savings explains 25% of income, and income predicts 25% of variance in saving. I will note with that last one, prediction is only in a statistical sense, not in a causal sense. So how much variance is left? 75% of the variance in income and savings is due to factors that we haven't investigated, okay? R squared is also known as your coefficient of determination. One thing to note, the correlation does not mean causation, okay? Correlation tells us whether, on average, the values on one variable are associated with the values on the second variable. Means that the variation in the scores of one variable corresponds with the variation in a second variable. Causation means that the variance in the scores on one variable create the variation in the second. We are not looking at causation. We just want to know if they're related, not that one predicts the other. Other important factors of correlations, a simple Pearson, we're looking at a linear relationship, so a straight line, okay? There are other types of correlations. Pearson's correlation cannot do curvilinear relationships, and as you can see from the graph, a curvilinear is exactly like it sounds. It has a curve in it, okay? Pearson correlations do not look at that. Remember, correlation coefficient tells us the direction of the relationship. Does one variable increase as the other increases? Or does one go up and one go down? And the strength, how much the variables are associated with each other. In looking at the correlations, we still follow our 5-step hypothesis testing. We state the null and the alternative, set the criterion for rejecting, calculate the test statistics, which we'll just be using SPSS, determine whether you reject the null, and then report your findings. Same as always. When we are looking at significant correlations, we're using a t-distribution. We are using the population symbol. The Greek symbol rho represents the population correlation coefficient. So when you're using it in the hypothesis, you want to always talk about the populations, not the sample. So we'll use rho in the hypothesis, and then we'll report it via R. So the null hypothesis is rho equals 0, meaning that there is no relationship between the two variables in the population. The correlation coefficient in the population equals 0, and the alternative is rho does not equal 0. There is a significant relationship between the two variables in the population. So what we are essentially testing is whether our correlation coefficient is statistically different from 0. If p is less than 0.05, we reject the null and find that our results are significant. And if p is greater than 0.05, we fail to reject the null and find that our results are not significant. So we will do one example. Some research suggests there is a relationship between stress level and eating difficulty. To test this, I randomly select 10 people and measured their stress level using the stress test, higher scores equal more stress, and the level of eating difficulty using the eating difficulty test, higher scores equal more difficulty. Use SPSS to compute your Pearson's correlation, identify the predictor and criterion, calculate and interpret the coefficient of determination, remember that's your R squared, and set the alpha at 0.05 and follow the 5-step hypothesis test. So now we'll use the 5-step hypothesis testing. So we're going to state our hypothesis. The null is rho equals 0. There is no relationship between the eating difficulty score and stress level in the population. And alternative hypothesis, rho does not equal 0. There is a significant relationship between eating difficulty and stress levels in the population. Set our criterion for rejection, alpha equals 0.05. And then we will need to calculate our test statistics. So we'll go to SPSS for this. So we can see that we have our 10 participants. They have a score on their stress level and a score on their eating difficulty measure. We'll go to analyze, correlate, bivariate. We will then put our 2 variables we're interested in our variables box. Our Pearson correlation is selected. And then this time we're actually going to go up to options and select means and standard deviations. Click continue and then click OK. We can see we get 2 boxes with our correlation. We get our descriptive statistics at the top, which we can see that our stress test mean score is 16.6 with 10 people. Eating difficulty score is 13.4. Again, our sample size is 10. And then we get our correlations box. So there are 2 different things we need to look at. This is set up in a 4x4. So there are 4 squares, 1, 2, 3, 4. And we can see on the top row, we have our stress test. And then in box 1, we have our stress test score by stress test score. That doesn't tell us anything. What we actually want is our stress test score by our eating difficulty score. So the top is our Pearson's correlation. So R equals 6.75. Our significance level, or our p-value, is 0.032. Okay, so in our step 3, we'll write down our R. We'll then calculate our R squared, which we're just going to multiply 0.675. We're going to square it, so 0.675 times 0.675 equals 0.455625. So our R squared is 0.46, and our p-value is 0.032. And then we'll make a decision. If our alpha is 0.05 is greater than our p of 0.032, so we reject the null hypothesis and conclude there is a significant relationship between eating difficulty and stress levels. And then we need to report our findings in APA style. So a Pearson's correlation was calculated to determine if there was a significant relationship between an individual's stress score and their corresponding eating difficulty score. A significant correlation was obtained. Our degrees of freedom is 8. Because it's n minus 2 equals 0.68, p equals 0.032, indicating that the greater the stress levels, the greater the subsequent eating difficulty. Given R is 0.68, R squared is 0.46, meaning that 46% of the variance in eating difficulty scores is explained by an individual's stress level. Here is the scatter plot, and that shows us that as stress scores increase, eating difficulty scores are also increasing. We do have some assumptions of our bivariate correlation. For every X point, there is also a Y data point. We randomly selected our participants. The relationship is linear, meaning it's on a straight line, and the variables are normally distributed. So those are our assumptions of a bivariate correlation. There are other types of correlations. So what we just talked about is Pearson's correlation, and it requires that both variables are continuous. There are 3 other types of correlations that we're going to briefly cover. The phi coefficient is used when both variables are dichotomous. So they have male and female, yes and no, tall and short, 2 levels. The point biserial correlation coefficient is where 1 is continuous and 1 is dichotomous. And the Spearman rho is when both variables are ordinal or ranked. So you got first place in a race. Is that related to your place you got in strength conditioning testing? So in summary for correlations, correlation coefficients are the basic statistical measure of the association or relationship between 2 variables. And there are several types of correlations. The Pearson's R, or the Pearson's correlation, which we are talking about, measures two continuous variables. Correlations tell us the strength and direction, and we can get the effect size through the coefficient of determination, or R squared. And the correlations are based on the t distribution.